So I'll talk about specifically about the PSyIR, which is the Cyclone Internal Representation in this talk. And well, this is not just my work, it's work of all the Cyclone team, which is mainly people from STFC, Hartley Centre, the UK Met Office, and the Australian Bureau of Meteorology. I'm going to divide this talk in 3 sections. First, I will explain what is exactly the PSyIR. Then I will talk about its internal structure and its API to interact with it. And finally, we'll talk about how Cyclone specifically uses the PSyIR to achieve its goals. So what's the PSyIR? So you've seen this diagram in Andy's talk. That's our vision of how the Cyclone ecosystem or well should work. So in the left-hand side, we have different front ends which define how the DSLs for different applications or the slightly different domains act, and we have several of them. And in the right-hand side, we have the different target languages that we might want to generate code into in order to produce the final code. So we have here in a scenario of that we go from multiple options to multiple options. So if we would want to make the solution specific to each of these all-to-all combinations, that would be very complex. It will grow exponentially, the complexity. So we had this idea to make a common blocks of concepts that would apply for all the front ends and all the backends we have here. And this also allows us to that the transformations that we do and we provide, if they are able to be applied in this common set of blocks, then it will be much easier to share these transformations between the different applications and backends. Also, let me quickly mention in this slide about the different funding that we got in order to develop the PSyIR. At the moment, we have funding, internal funding from UKRI to study collaborations with the US Exascale Computing Project. And we also got several fundings from the European Union through ESiWACE and EUROEXA in order to develop some of these backends. That is the whole vision, but if you think how a single workflow in Cyclone works, as Andy mentioned, we care a lot about the separation of concerns between the domain-specific knowledge and what the scientific people working in the domain do, and the parallelization and optimization steps. We think this should really be separated and decoupled in the code. And as you can see here, the domain-specific knowledge is mostly described and embedded, or completely described and embedded in the Fortran code, which the front end is going to parse. This means that probably the domain person doesn't really need to know anything about the PSyIR. It can completely live in the Fortran or in its DSL world, while for the HPC expert, the person who wants to do these programmatic modifications of the code in order to add parallelism and optimization, for this person knowing about PSyIR and its transformations, it's going to be very important. So just to sum up this brief introduction, the PSyIR is this intermediate representation which is language independent, because we want to end up producing code in different languages, in different backends. Is it mutable? Is it a mutable representation? That's, I think, quite sensible for us, because we end up transforming the code, but that's not the case in some compilers or syntactic analyzers, which are not mutable. And in our case, we decided to do our PSyIR also domain agnostic, so it doesn't really care if it's part of a DSL or not. However, its infrastructure is very easy to extend in order to create domain-specific DSLs in top of it. And that's basically what Cyclone does. It creates domain-specific DSLs using the PSyIR infrastructure. So the next thing I'm going to talk about is its structure. The PSyIR is structured as an abstract syntax tree with a scope symbol tables. I don't know if you are all familiar with this data structure. This is a very common structure in compilers theory. I made here a representation of an abstract syntax tree of this code in the left-hand side. Basically, what the abstract syntax tree, or AST for short, represents is just the basic concepts available in the code without all the extra syntactic notation that make it usable for humans, but it's not really needed for an internal representation for a computer. So it gets rid of all the punctuation and line breaks and these things. You can see that this relate one with the other. So you can see we start with a Fortran module, which in our PSyIR we define as a container. Then inside the module we have a work subroutine, which in this case it's represented as a kernel because we think about computational kernels in Cyclone. And basically from all of this, there is just really 2 lines and execute things. The first one is this assignment, which is represented here in the AST, which assigns this literal into a reference. And then we have a call, which 2 parameters, which you can clearly see in the tree. And the second one has inside its unary operation has a binary operation. In addition to that, we have information about the symbols, and the symbols are organized in scopes. So if you like to think here in Fortran, the argument and the value are part of the subroutine scope, so they are linked to the kernel schedule scope, while the sub library module and work all are part of the module scope. So they are linked here in the container. So that example hopefully looks very easy, but unfortunately that's not always the case, and that's because the programming languages are thought to be easy to read and write for programmers. So they are very compact and they use syntactic constructs to make things very easy to read and write for humans. But the ASTs are not. They are designed to be easy to read and write and manipulate for programs. Therefore, they don't have, or we prefer that they don't have all syntactic sugar like else if, do while, select, switch, where, and other statements. We prefer to just have one branching and one looping nodes or concepts, and then canonicalize all the other syntactic expressions into these ones, so they can become very big very easily. Another thing I want to mention here is that every time in the PSyIR that we can have multiple expressions. For instance, here we have value equals 1, but we might have several expressions in this block. We organize this inside a schedule. So for instance, the if body of the condition will be a schedule, the else body will be another schedule. So yeah, we know that ASTs can be very complex. So maybe the most important thing that our API for our AST provides is a view method. This will help a lot to see what's the current state of parsed code or a modification that we just did in the code. And it's a very simple thing, which is that every node and every symbol table in the PSyIR will have this .view method that will produce a textual representation of what's going on. So in this example here, you can see that I'm visualizing the container symbol table, which is this symbol table here, the kernel schedule symbol table, which is this symbol table here, and then the container node, which is this, and it visualizes the whole tree. Also, as I said, this can become very big, so I would not recommend them looking at them at black and white, because they can be difficult to navigate. So we have this optional dependency. It's a Python dependency. You can install it with pip install 10 color, and it colorizes the tree, and it really helps a lot to navigate the structure. Then the next thing that you probably want to do is know how to navigate the tree. We have two kinds of operations for that. One is what we call homogeneous navigation. This means that these operations are available for all the nodes in the tree. Doesn't matter which kind of nodes they are. So for instance, here I'm doing an example of this homogeneous navigation with the binary operation, which is placed here. And basically there are three operations. The parent that navigates to the one node upwards in the tree. In this case, it returns you can see here the unary operation. The root that goes to the root of the tree, and the children, which returns a list of each of the children available for that specific node. So again, for this binary operation case, it returns the reference and the literal, which are the children. Also, all of the nodes can have these two methods, searching methods, when you don't know exactly where things are, but you want to find, for instance, using the walk, all the elements of a specific type below a certain node. You would use the walk method, or upwards from a specific node, you would use the ancestor type method. So as I said, these are all available to any node. But then we have another class of operations to navigate the tree, and these become very handy when you already know what node you are in, maybe because you just walk into these trees and said what type you are expecting it to be, or maybe you just created this tree. Then we offer these properties that are only available for that specific kind, but are much more expressive of what you are doing. For instance, for assignments, we provide a left-hand side and right-hand side semantic navigation operations. For the conditionals, conditionals and loops are not here in this example, but still, I think it's where these semantic navigation operations are more useful. For conditionals, we have the condition that gives you the part of the tree that represents a condition, the if body that returns on a schedule representing the if body, and the else body, which is optional. Not all ifs have an else, but if there is something here, it returns you on a schedule. Similarly, the loops have a start expression, a stop expression, a step expression, and the loop body of the loop. Another thing that you may want to do is find the symbols. To find the symbols from any node in the code, the first thing you have to do is find in which scope they are situated. So for instance, here, using again as an example the binary operation, if I do scope, it navigates to the first available inner scope, which is the kernel schedule, and it would return this symbol table. But in fact, reference or anything here can live in any of the scopes encapsulated outside. But you don't have to, as a user, to record up all the symbol tables, because and once you found the inner scope symbol table, the lookup method that will give you which symbol are you looking for, giving a name. So for instance, again, with the binary operation example, if we do a lookup for library, it will not find the library in the symbol table, records up to the next scope and find the library symbol table and return that it's a container symbol. Finally, similarly to the semantic navigation methods, we have some of the nodes have some properties to return you a symbol which is very related to the node. For instance, the call method can you return with the call.routine the routine symbol that it refers to, or any reference with the reference dot symbol returns you a pointer to the data symbol in the symbol table. So as you can see here in the symbol tables, for instance, the binary operation scope symbol table, every symbol has a type in PSyIR. It's a type system. And there are different kind of types that we represent. Maybe you all will be familiar with scalar arrays and structures or derived types if you come from Fortran. But maybe you would not know, you will see a lot of these deferred and unknown. In this case, the deferred are symbols that we have found in the code, but we have not found the declaration. This happens often because by default, when we import something from a module, for instance, we just see the symbol, but not the declaration. And that's okay in most cases for Cyclone. You can still do transformations with it. You don't need to know the type. But if you really need to know the type for specific transformations, these deferred symbols can be resolved by parsing the library where they come from. It has a specific resolve method that gets this information back. The unknown case is a bit different. It still finds all the symbols, and in this case, it does find the declaration, but there is some attribute that Cyclone doesn't understand. So again, it's still enough information for some of the transformations, but some more complex transformations might not know with unknown symbols. Then here for scalars, for instance, we have two more properties, which are intrinsic types and precisions. And you will see a lot of time in the precision field, we have this undefined parameter. Undefined means that the source code is not providing specifically what is the precision, and that it will generate this the same. It will let the compiler decide what the precision should be. That is usually is compiler or implementation specific. For most of the scalar types, you can get them in Python by importing them from Cyclone PSyIR symbols. We have predefined most of the scalars that you would need. But for more complex type, you have to build the type yourself. For instance, for an array, you would use a scalar type and a shape of the array. In this case, it's a two-dimensional 10 by 10 array, and you create this type. And there's also support for data structures with different fields with different types, and we also support having public and private visibilities similar to what Fortran and C languages offer. Then there's node creation. That's how you create a node. Before going to node creation, let me say that this is only used for very low-level manipulation of the IST. You probably should avoid this if you have a transformation that already do what you want to do. But if there is no transformation that does it, you have the option to create nodes. I know I'm a bit short on time, so I will not go a lot into detail. Just mention that not all nodes are valid children of other nodes. A quick way to see which nodes are valid children is to use this underscore children valid format field, and it will give you a description of what nodes are valid. And then that we support two modes of creation, which is quite typical in IST. One is the top-down creation, which is starting from the top node and start creating the node downwards. And the other is bottom-up, is starting from a node, leaf node in the bottom, and start creating the trees upwards. I know it's a very dry to see the documentation of the API in the slides. You will become much more familiar with this when you do the hands-on exercises, where you will be able to play around with this API. Last couple of things I want to mention. One is code blocks. We have code blocks in the PSyIR in order to represent nodes that are unrecognized and so are language specific and unrecognized. So that is in an example. So we have here an example of PSyIR3, which at some point has a code block, which it says it's a Fortran part of the code, which it has not parsed, which is a write statement. This is because, well, we don't usually care too much about higher level things and I/O. We care about data accesses and algebraic operations mostly. So we don't spend a lot of time trying to parse every single bit of Fortran into our PSyIR. Only the things that we think they are relevant for the computation. So usually, if you have these code blocks, you can still apply some transformations, but probably not all of them. So if you have code blocks in your kernels, you probably want to get rid of them. If you have code blocks in the higher level algorithm descriptions, it's usually not a problem. This, together with the unknown type that I described a moment before, makes for a quite strong solution that lets you usually parse any code. It doesn't fail, but it just parses the parts that Cyclone is sure that it will understand. Finally, as I said, the typical way you have to manipulate the PSyIR without going to low-level details is to apply transformations. So first, you need to know which transformations are available. One way to get the available transformations is using this transinfo option info object, which has the list parameter, which will give you a list of all the possible transformations that you have available at a certain time. And then you have to do these 4 steps. One is choosing which node you want to apply the transformation in. Second is choosing which transformation do you want to apply. Third, this is an optional step, is to validate if the transformation can really be applied into that node. And the final step is to apply the transformation. Now, you will see that in the examples and in some Cyclone snippets, we don't use this transinfo, and that's because this is being refactored at the moment. So if you don't have access to a transformation through this object, you can directly import in Python, if you're familiar with Python, a transformation by looking specifically at the folder or the module where this transformation is available. So I'll finish with some examples of how Cyclone uses all this infrastructure. And the first is that, as Andy mentioned, Cyclone has different levels, and there's already a big distinction here. One is that the algorithm and the kernel levels come from existing code. So Cyclone just parses this code and has the possibility to modify them, while the parallel system is fully generated by Cyclone. So Cyclone generates the PSyIR for the parallel system from scratch. The second difference is that we still don't fully support PSyIR for the algorithm because we really don't do big transformations in the algorithm. We just change how specific calls are called to what they call. But we support the PSyIR in the parallel system and in the kernels. In fact, in the parallel systems, we add more concepts into the PSyIR. We add all the parallel concepts like directive, global sums, halo exchanges, and other concepts. And some of these also have a specific logic that is domain specific from the DSL where they come from. However, for all these new classes, not all of them can be generated using the PSyIR backends. And I will talk a little bit more about this when I speak about OpenCL. I will speak in detail about OpenCL in my talk on Wednesday. So finally, here is an example of a script where when you execute Cyclone to a specific source code, you are able to specify a script. And this is the simplest script that I could come out to get access to the side layer, PSyIR. In this case, the side layer PSyIR is found by getting the schedule of a specific invoke. You will see more about that in the hands-on. And to get access into the kernel PSyIR, you then have to search for all the coded kernels inside your invoke schedule. And you have this method called get kernel schedule that will return you the internal kernel PSyIR. So summarizing all that, in Cyclone, you start with an algorithm description, and you use Cyclone to automatically generate your parallel system layer, which by default will be very simple, just the loops iterating around the kernels. So here is the same example. Once you have that, you can use the PSyIR probably through a script with transformations, but if you want, by doing low-level manipulation of the AST in order to transform this into the optimized parallel PSyIR that you want to do. In this case, we apply 2 OpenMP transformations in order to add this OpenMP directive around the loops. And once you are happy with your optimized PSyIR, using a backend, you can generate this back into code. In this case, it produces this Fortran code. There is some limitations of what we can do at the moment. So in the front end, we can do direct PSyIR creation, as I explained, with the API calls, and also parsing Fortran code. But in the backends, we are more limited. So Fortran at the moment works with all the front ends, but the OpenCL backend at the moment just works with the GeoEngine kernels, and the PSyIR backend at the moment just works with the Nemo front end. However, we are working in order to extend this and also bring support to C and C++, which at the moment is quite limited and only available to support the OpenCL. So yeah, that's my last slide. I know that was a lot of information, but if you remember something from this presentation, is that PSyIR is the internal representation, and it's the building blocks at the core of Cyclone. The PSyIR is mutable, and this is by design. Is to allow the HPC experts to do manipulation of the source and to encode their optimizations and transformations to programmatically apply these transformations into different code. It is also language independent. This means that it can produce code in Fortran, OpenCL, or in different backend languages. And the PSyIR and Cyclone come with a list of transformations, which are the easy way to do manipulations in the PSyIR tree. So that's the end of my presentation. There is more information in the read the docs of Cyclone. That's cyclone.readthedocs.io latest /PSyIR. And if you have questions now, I'm happy to take them, or you can contact me at my email address.
Thank you, Sergi. There are a couple of questions that have been posted. I don't know if you can see Google Docs. If not, I can read them out for you. So one was,
I don't have the Google Docs open at the moment.
Yeah. So do you want me to read it for you?
Oh yes, please.
Okay, sorry. Yeah. So I'll go with the last one first that Will's asked. He did ask a question earlier, but he's finding PSyIR still being a bit mysterious to him. And his particular question is, if you don't provide any PSyIR transformations, so there are no transformations into PSyIR, will it produce anything sensible? And he's actually said by making some default assumptions. So I guess the question is if you do something into PSyIR and then you do a backend, what will it do?
Yeah. So let me go back to to this example. So if you don't provide any transformations in a PSyIR which has been generated from scratch or by Cyclone, for instance, for a parallel system, you would still have a PSyIR tree looking like that. So it's maybe not optimized or maybe not parallelized, but it's a tree. So you can send this PSyIR tree into the backend, and it will generate something, not this code with the OpenMP parallel, but it will already generate the loops. I don't know if you can see my pointer. It will generate the loops and everything that is represented in the PSyIR. And I agree it can be a bit mysterious, the PSyIR, and takes a bit to get used. I would recommend using the view option a lot at the beginning, just to see what's your current state, and maybe apply a modification. Use the view method again to see what's the output, and until you get more familiarized with the PSyIR.
Thanks, Sergi. There was someone asking whether we could give a quick example of a transformation. I don't think that's going to be feasible now.
Well, that is really an example. So, for instance, here we iterate all the children of the schedule, which we know they are all loops, and we apply the OpenMP2 transformation, which basically inserts before the loop this OpenMP directive. That's a very simple example of applying a transformation, but I'm sure during the hands-on there will be several examples of doing transformations and applying them.
Yeah, thanks, Sergi. I forgot to see that. And yes, over the next couple of days, there'll be lots of examples of transformations anyway. Hopefully that's answered your question.